Okay, there we go. Things were paused for a second. This week we are going to talk all about determinants, and then some more determinants, and then some more determinants, and then we're going to talk about vector spaces and what that means. So we've talked a little bit about determinants already, and in particular, right, we talked about the determinant of a 2 by 2 matrix. So if I have a 2 by 2 matrix, say A is some A, B, C, D, we said that the determinant of A is equal to the product of the main diagonal minus the product of the second, that's the wrong letter. Yes, there we go. So we take those diagonals and we multiply them, right? This guy, hey, hey. And that's pretty straightforward, right? Now, when we start to get into determinants of larger and larger matrices, this becomes less of a simple, straightforward, let's just take the product of some things and throw it together. And we kind of gotta boil things down. So essentially, what we're going to end up doing is we're going to boil things down until we get 2 by 2 matrices, find the determinants of those, and use that. So here's how we're going to do this. So just a reminder, so here's one way that we could talk about our matrices. And just to remind, so we have each of our positions here, right? A11, A12, as we go this way. These are the J's change because the J represents the column, right? Again, we always list this by row and then column. And so we'd have, if I'm asking about something like the ith row would be something like this, right? The jth column would be some column here. That's all that means. And so that terminology is going to come up a little bit as we move forward. So we've got to introduce a couple of new ideas before we can get into how we're actually going to break down our matrices into 2 by 2 matrices to find a quick determinant. And the first thing we need to talk about is this Aij matrix. Now, the Aij matrix is a matrix that happens when you remove the ith row and the jth column. So here we want to find the A32. So that means that we want to find what the matrix is when we take away the third column, or the third row, and the second column. So I'm gonna highlight those. I'm not gonna cross them out just because we may end up using them at some point. So here we'll make those. Let's fix our coloring here. Yeah. Let's see. We'll make you red. Ay. I've been using a different program to take my own notes, and it works better for taking my own notes, but it doesn't record videos, which is terrible. So I gotta come back to this. Not that I hate it. I enjoy this. All right, so our second column is this guy here. So we're going to pretend he doesn't exist. Our third row, that's this guy here. We're going to pretend he doesn't exist. And all we're going to do is we're just going to squish everything. It's like we're deleting that row and that column, and we're just going to squish everything back together. And our remaining A32 vector, or matrix, let's throw that one out there, is 1, 5, oops. Let's, do this with a pen, not a highlighter. Is 1, 5, 0, 2, 4, -1, 0, -2, 0. So we're going to end up using this idea over and over again as we start to break down our vectors. And by vectors, I mean matrices. Anyway, so the next thing that we're going to need in order to help us with this breakdown idea is something called a sign matrix. So the sign matrix is not a matrix that contains numbers of any kind. All it does is indicates a sign. And so the first position in any one of these is always going to be a positive. And then what we're going to do to figure out where all of the other signs are, we're just going to alternate from positive to negative as we move along, making sure that none of the adjacent positions have the same sign. So if we're gonna, so here's the 3 by 3 matrix, you can see. So as you can see here, next to all the adjacent positions, so adjacent means immediately to the left or below or right, up, down. We're not talking about diagonally, that doesn't make a difference. But just up and down, left and right are our adjacent positions. So you'll see I have a positive always in this position, and then I'm going to go negative, positive, and then because this one's a positive, the one below it needs to be a negative, and then we'll alternate and so on and so forth. So if we find the 4 by 4 sign matrix, again, I'm going to start with a positive in the 1, 1 position, and then I'm just going to alternate. So I have a minus, a plus, a minus. Now you might think, hey, I just alternated along there. The next thing that would come along is a plus, but because this is a plus, I can't have the position right below it also be a plus, so it's going to be a minus. So minus, plus, minus, plus, and then again plus, minus, plus, minus, lots of fun, right? You'll also notice that the diagonal is always the same sign, whether you're talking about the main diagonal or the opposite diagonal, they're always the same sign. Kind of fun. But that's what it is. So the Aij matrix and the sign matrix together are going to give us what we call a cofactor of A. So the cofactor of A is going to be defined by, so for any position, so if I want the Ij position, I'm going to go find the sign of that Ij position in the sign matrix, and then I'm going to multiply that by the determinant of the matrix that's left over when I cross out the I and the J columns and squish that thing back together. Hope that kind of makes sense. So if we sort of use this idea up here, we already have the A32 column. So if I wanted the cofactor of 32, this would equal, so I need to go find the sign. This was a 4 by 4 matrix. Whoa, hold on. Goodness, that scared the life out of me. Anyway, all right. So I think I was saying something about the size of matrix A being a 4 by 4 matrix, which means we need to use the 4 by 4 sign matrix to determine the sign of our A32 position. So the A32 position, so that would be the third column, third row, second column. Turns out it is a positive. So we would have a positive times whatever the determinant of our A32 matrix is. Now we'll get into what that determinant is in just a minute, but that's sort of the idea here. So the determinant itself might be positive or negative, and that's not what the sign matrix is controlling. The sign matrix is just controlling whether or not that determinant itself is multiplied by a positive or a negative number. Hope that's clear. Okay, I think that's it on this page. Let me double check. I believe so. Okay, remainder? Yes. All right. Let's do an example. So we just found, this is a different matrix. Yes, this is a different one. We're actually going to find the, we're gonna cofactor expand, or find the cofactor of the cofactor. Don't worry about it. So this was, if we go back to the previous one, was the A32 vector, or I'm doing it again, matrix, but we're going to ignore that and we're going to pretend like this is not. So this is a new A matrix. So for the cofactor of the 3, 2 position, we need to determine a couple of things. Now, instead of writing the sign matrix somewhere else, what I'm going to do is I'm actually going to put a little sign up in the right corner of each of these positions to indicate whether or not that position is a positive or a negative for our cofactor. And that way I can kind of keep track of it. So I'm just going to put a little plus here, a little minus here, so on. And this is a 3x3 matrix. So there's our sort of our little sign matrix sort of superimposed behind our A matrix. So our cofactor for C32 in the 3, 2 position, that's this guy right here. So we'd have a negative. So the cofactor, oh, that's a terrible color. The cofactor of 3, 2 is equal to a negative, just because that is the actual sign of the position, times the determinant of the A32 vector. Now, we haven't found the A32 vector, so let's go back and find the A32 vector. Let's find a better green. Hey, that's better green. So the A32 vector is what happens if I get rid of the third row and the second column and squish that thing back together. It's going to give me a vector of 1, 0, 2, -1. The determinant of this, so the determinant of our A32 vector is 1 times -1 minus 2 times 0, which is 0. So we get a -1 here. And that means that our cofactor for the 3, 2 position, so our cofactor for the 3, 2 position is negative of -1 or a +1. And hopefully that makes sense. So how we're going to use this idea of our cofactor expansion to find our determinants is by expanding either across a row or across a column, which means that we're going to find all of the cofactors in one row or all of the cofactors in one column, and we're going to multiply them by the positions in that column or row. So here's what I mean by this. So if we take our buttons are hard. So for the determinant of A, if we go across the ith row, what we're going to do is, so here's our, right, these would be our i's, these would be our j's. Across the ith row means that we're going to take whatever's in that row. So here's our AI1, here's AI2, AIN. And again, this needs to be an M, but it needs to be a square matrix. If it's not a square matrix, we got issues. So we're going to take the constant or the values in each of those positions and multiply them by the cofactors that correspond to each of those positions. Same thing if we go in the J direction. So maybe here's my J column. That's a terrible J column. Let's pick one over here so there's not already a thing in it. So this would be the A1J, A2J, all the way out until ANJ, right? And those are the positions in the J column. Now, it does not matter what column you pick. It does not matter what row you pick. Any of those columns or rows will give you the same determinant, but there are some ways to strategically go about this so that we have, so that we kind of have a little bit less work to do. So this is nice because at least now we can find the determinant of an n by n matrix. But the problem is that depending on the size of our matrix, this could take us a while, right? If I have a 3x3 matrix, at least I only have 3 of these products I need to find. So I need to throw in 3 cofactors and multiply them by the constants. But if I have a 4x4 matrix or a 5x5 matrix, as this thing gets bigger, I have more and more pieces. And each of those pieces, as we break this down, gets smaller, but not always in a way that gets us right to a determinant of something. Sometimes we have to do a cofactor within a cofactor expansion in order to be able to get a determinant that we need. Hope that makes sense. Ooh, also, separate notation that I haven't mentioned. Sometimes we will write the determinant like this. So we could say the determinant of A is equal to, and we'll use, instead of our matrices having the extra little bracket like this, if they look a little bit more straight, if they're just straight up and down, this means, that means determinant. So sometimes you'll see that instead of writing determinant and relabeling each of these matrices as we break it down, instead of naming them, we'll just write it like this, where we put those square brackets, not square, straight brackets, and then our matrix, and that means determinant. So let's try this out. So, oh, right, I got sidetracked. So what might be ideal to look for in picking a row and a column? Well, I don't know about you, but when I see multipliers and I want to add a bunch of stuff up to make things easier, if I have 0 multipliers, then things go away. So it makes, hopefully it makes sense that if we look for columns or rows with lots of zeros, that makes this a little bit easier. So we may want to pick, a row or a column that's got as many zeros as possible so that we're multiplying by 0 and we don't have to necessarily find as many determinants of smaller matrices. So let's take our situation up there and see what happens. So let's go. All right, so this is the same matrix as we used in the previous example. So we already found one of the cofactors. So we actually have 2 different choices of what would be ideal for doing a cofactor expansion. If you look here, so on the bottom row, you see that we have 2 zeros, but in this last column, we also have 2 zeros. Now, to save ourselves a little bit of work, because we already know what the cofactor expansion is of 3, 2, we might as well go ahead and do a cofactor expansion along the bottom row as opposed to along that column. Right, so we already know for 3, 2, which is this position here, so might as well sort of have a ball there. So I'm going to write this out as in terms, and I'm going to erase a bunch of that garbage there to get us into a better place. All right, so we're gonna expand across this row here, which means that our cofactor expansion, or our determinant for A, is going to be our A 3, 1 position, or that value, times the cofactor of the 3, 1 position, plus A 3, 2 cofactor of 3, 2, plus A 3, 3 cofactor of 3, 3. Now we already determined that this is equal to 1, but just in case, I'm going to write this out. So each of these cofactors, again, we're going to need our positives and negatives. We need to know that for our cofactor expansion. And then we need to know whether or not what we're multiplying by. So again, I'm not going to put the positives and negatives above every single one of the things in this matrix, but the bottom row, if we go back and look at the sign matrix, this would be a plus, a minus, and a plus here. So in terms of our cofactor, or our determinant, so here's our determinant. So the determinant of A is equal to, so our A31 position is 0. Our cofactor of 3, 1 is what happens when we take that sign, which in this case happens to be a plus. And notice I put that plus in parentheses so that I know that I'm not actually adding 0 to something, I'm multiplying by that positive number times whatever the determinant is if I cross out these 2 rows, or that first row and the last column, right? So the 3 tells us cross out that column, the 1 tells us cross out that, and I'd have the matrix 5, 0, 4, -1, and I'm putting it in the straight things to represent that this is telling me I want the determinant. Now, I don't even have to figure out what that determinant is because I'm going to multiply by 0, so that thing's going to go away anyway. And the next one, so let's go back here. Let's put our positives and negatives back because they went away. The next one, so then I'd have plus now my A32 position, which is -2. and our cofactor of 3, 2. Now, nicely, we already figured out what the cofactor of 3, 2 was upstairs earlier. We figured out that this was equal to 1. And so we don't need to do it again. If we already did it, don't do it again. That seems silly. So that gives us a -2. And then lastly, we're going to take our A33 position. Oh, and then what did we do? So, oh, right. I didn't need to worry about the negative in this case because we already baked that into our cofactor, didn't we? Never mind. All right, and then lastly, we have our A33 position, which again is a 0. That position would have a positive term for our cofactor, or a plus as a multiplier for our cofactor. And then again, we would cross out the 3 row with the 3 column. We'd take the determinant of 1, 5, 2, 4. But in this case, we don't even care about it because we're multiplied by 0. So it turns out in this case, the determinant of A is equal to -2. Yay! All right, we're going to do another example in the next video and have a party.